if we are stuck with mechanism, yeah, the first thing that I would say to do is take a little step back and understand completely the definition between the definition of electrophile and nucleophile. Nucleophile, electron pair donor. Electrophile, electron pair acceptor. So electron pair donor means that it's everything that has lone pair of electron, maybe a delta negative, maybe a formal negative charge because it gives away electrons, while the electrophile would be electron pair acceptor, so could be something delta positive or an actual positive charge. Let's have a look at all of the functional groups seen so far and try to predict what they could react as. Let's take an alkene. Dipoles, one thing very important, they arise due to difference in electronegativity. Yeah, so that's what we needed to work out. So if you have an alkene, there is no difference in electronegativity actually, because we have just carbon bonded to other carbons. So, and the carbon and hydrogen, which we know they have the same electronegativity. But what we have, it's a region of high electron density. We have a lot of electrons, two in here and two here. So between those two carbons, we have this region of high electron density. So we know that it could only react as a nucleophile. Well, because it has electrons, it has a pair of electrons that could be given away. And this pair of electrons is in the p orbitals of these two carbons, or better, in this pi bond. Let's look at the second functional group that you probably come across in AS level. So let's do the simple one. Let's do this one with a chlorine attached. So the thing we need to think about is there any difference in electronegativity or any region of electron density? Well, yes, this carbon, it's slightly positive because it's bonded to chlorine, that it's slightly negative. So the most likely reactivity would be carbon as an electrophile. Good. This could also be a nucleophile maybe, but then think carefully. Okay, wait. How would that happen if a chlorine can't really have more than one bond? How is it possible that the chlorine would form another bond? Somehow this carbon-chlorine bond would have to break. And is that something you've seen before? Not really. Then it's likely not to be a mechanism. Okay, because also a way to learn organic chemistry is always to just do mechanism over and over again to get really, really familiar so that you actually would recognize if it's something that you've seen before or not. But that's why these, like haloalkanes, it's most likely to react as an electrophile. So these are carbon positive. It could be an electrophile. Good. In this case, well, we have notice what thinking we do all the time is that where is the electron density, where are the lone pairs, is there any difference of electronegativity? That's just the thinking to do. And well, we know that the oxygen and it's a lot more electronegative than the carbon and the hydrogen. So actually, yeah, it could react as an electrophile. Normally the carbon, because we know that hydrogen, I mean, we're talking about organic chemistry, reactivity of carbons and making new carbon molecules. So, I mean, we're not really focusing on hydrogen, but on carbon, yes. That's why absolutely the carbon would also react as an electrophile. But because the oxygen is slightly negative and it has lone pairs, it could actually also react as a nucleophile. So here it depends on what it's reacting with. Because of course, then organic chemistry is never reacting just with the one, I mean, it's not one molecule reacting together, isn't it? We always have two. That's why we need to do the analysis for both substrates that are present. Let's look at the next one. So we always start with looking at the region of electron density or electronegativity. We know that this carbon is going to be slightly positive because oxygen is always slightly negative. So guess what? All of this, yeah, the dipoles are spread in this way. So this tells us that this carbon, it's all it's an electrophilic center. So in all of these cases, so for aldehydes, ketones, and carboxylic acid, this is going to be an electrophile. And actually, there are a lot of other functional groups that do the same. We have amines. We have, amides, acyl chlorides. I don't want this color. We have acyl chlorides. Notice how, if we do this analysis of difference in electronegativity, we always get that carbon as a slightly positive. So when there is a carbon attached to a double bond or attached to something electronegative, this is going to be the most likely reactive center, is going to be our electrophile. Okay, so it's common for most of functional group, actually. We have 5 different functional group here in this slide. And for all of them, they, like, this carbon would react in the same way. It's an electrophilic center. So the analysis really help us identifying what could react, because then, of course, it depends what all of these molecules are reacting with, if it's with an electrophile or a nucleophile. And we would do the same analysis. So for example, let's say that any of these molecules that we've listed is reacting with the sodium hydroxide. Well, we know that sodium hydroxide dissociate as a sodium ion, and the hydroxide ion, hydroxide has a lone pair of electrons, actually 3 of them. So this is definitely going to react as a nucleophile. But what if we have like an acid? Well, we know acid partially dissociate. So what could be the most interesting reactive thing? Well, it depends. We could have the chlorine. If we're reacting with an electrophile, then the chlorine would be the reactive part of this molecule, and it would react as a nucleophile. But if we have a hydrogen, then, well, that's actually the most likely thing that it could react. So if we are reacting it with a molecule that it's slightly negative or something, this would be our electrophile, because it has an actual positive charge. So the analysis, we need to do it for every molecule, but not only, of course, the organic molecule, but also the other reagents like sodium hydroxide, hydrochloric acid, or whatever we're given. So if we look at an example like this one, where we have an alcohol and an acyl chloride, this is the type of analysis that we need to do. So an alcohol, well, this could be a reactive center, absolutely, because it's slightly positive. But then what could it react with? The oxygen reacting with the carbon, like what would it form? It would be a little bit of a weird one, not familiar. So let's look at the other options. We have the alcohol here, that is a nucleophile, could also react as a nucleophile. And then we have this carbon attached to a double bond oxygen and a chlorine, which, as we've seen as the most common reactive center, it's an electrophile. So this is probably the most likely part of the molecule that react. So it would react with the nucleophile. And with this analysis, by thinking, okay, which parts of the molecule could react together, then we may be able to work out a mechanism. For example, if we've identified that the nucleophile, it's this oxygen, the alcohol, because it has a lone pair, and this is our electrophile, we can actually work out the first curly arrow, which is a nucleophile to electrophile. And then we always need to think about, okay, what happens now? Well, carbon can't have more than 5 bonds. It has already more than 4 bonds. It has already 4 of them, which means that as a new one forms, the weakest one will break. What's the weakest one? Always the pi bond. And we know that oxygen has the ability to take electrons onto itself, which means that this step could occur. It's really, really important to see these curly arrows as, okay, this means a new bond. So basically you're translating this curly arrow in an actual bond. So the covalent bond is always shown with that line. Okay, so let's do that first. Okay, we have the oxygen. The hydrogen is still there. But then this lone pair of electron is now attached to this carbon, which is the electrophilic center. So what's attached to this carbon? We still have the chlorine. We still have a methyl group. And then what has happened to this? Well, the electrons, so those electrons have moved on to the oxygen. And now you can think about charges. So if those have gone onto the oxygen has now has a negative charge. Then you can think, okay, is there any other charges that are present? Actually, yes, because this oxygen now has 3 bonds. If oxygen has 3 bonds, or if it formed a dative covalent bond with this carbon, it's kind of giving away its electrons, so to form this dative covalent bond, so it would have a positive charge. Also, because if you have a negative charge because of the movement of these electrons, you're going to have a positive somewhere else, because overall, if all of this is neutral, then also the other intermediate would be neutral. Okay, the charges are kind of always maintained. The thing to think about is that, okay, could this negative charge do something? Or what are the options? Well, it could react with something else, but then it would keep a very awkward group here, isn't it? Like, okay, what is oxygen, and chlorine? Have you even seen a functional group like this before? No. So probably something else is going to happen. But what functional group could this be? Well, you have oxygen, another oxygen. Oh, wait, those are esters. Maybe it's an ester. How would that form though? Because the options here are two. Either this could react with an H plus and keep this very awkward functional group, or the double bond can reform. If the carbon double bond reforms, it's because there is what it's called a leaving group. And the leaving group is just a molecule that it's relatively stable on its own, or a bond that it's likely to break. So this carbon chlorine, it's pretty polar, so it is likely to break. While the carbon oxygen, well, no, because it just formed. Carbon, it's not likely to break because there is no dipole there. So the steps here are going to be reformation of the double bond, and then the leaving group, it's gone. Following along those curly arrows, now we have carbon double bond has reformed. This bond has broken, but this oxygen, it's still attached. So I'm just going to try to keep a bit the angles of the molecule. So this trigonal planar, so we keep this angle. We still have that hydrogen attached with the positive charge because we've done nothing to it. And then what do we have here? We still have that arrows attached, the carbon groups attached. Okay, so what else do we have? Oh, the chlorine is there with a negative charge. So we don't need to write a plus, but let's just write it over there floating around, chlorine with a negative charge. And then you can just think about what is now the most likely part of the molecules to react. I mean, we know that we don't really want to keep charges, so we might want to get rid of these charges. If you're not sure what could happen next, always keep in mind the functional group that you're familiar with. Here, well, we could have a chlorine, oxygen, and attached to another oxygen, but I mean, we haven't really seen that. So what functional group is this going to be? An ester, which means that we want to make the ester. So sometimes also when you are completing flowcharts, you actually have the final product. So you can have an idea of, okay, what would be the reactivity, like what is the final product really. And we know that the final product here is going to be an ester, because this is really the only functional group that we're really the most familiar with, because otherwise I don't see how the chlorine could bond with another oxygen, or oxygen with 4 bonds. We've never really seen it. It's not possible. So that won't happen, which means that if we want to get to this, oxygen with its usual 2 pairs of electrons, 2 bonded pairs and 2 lone pairs, well, we must get rid of that hydrogen. In fact, and we know also HCl, it's a pretty common side product. This is what's going to occur, the chlorine bond with the hydrogen, and the hydrogen is what gives back the lone pair to the oxygen, which means that this side product is HCl, and then we have an ester. In fact, this is actually a mechanism that it's really, really important to be familiar with. And it's probably one of the most complex because there are several steps and we need to know about this leaving group, but this is called the addition elimination mechanism, because we have, as you can see, the addition of an, in this case, an alcohol to an acyl chloride, and then we have elimination because we're getting rid of a leaving group. And addition elimination, we see it a lot in making esters. So the type of the molecules that would undergo this mechanism are acyl chlorides, like we've seen here. We have also acid anhydride. And acid anhydride, they look something like this, because, I mean, their activity of this carbonyl, I think now we're familiar with, because we see that it's common for pretty much all of the functional group with a carbonyl. But this is a really good leaving group. Yeah, that's why it would undergo the same mechanism. Okay, so as acyl chloride, acid anhydride, even carboxylic acid could do this mechanism. In fact, it's the most common one to make esters. Okay, so to make a little summary, to make those a bit bigger functional group like esters, as well as amides. So ester being carbon double bond oxygen with an oxygen, and then, you know, the other like carbonyl groups, we would have acyl chlorides or acid anhydride or carboxylic acid. Yeah, all reacting with, let's do our group, just to keep it general, reacting with an alcohol. Wait, I'm getting lost here. Reacting with an alcohol. Okay, so same mechanism. And guess what? If instead we have these three molecules, but we react them with an amine, which could be primary in this case, or it could also be a secondary amine or a tertiary amine, we would get amines, which look something like this. Yeah, and then we can have either hydrogens, or we could have more substituted, so R groups instead of the hydrogen. Mechanism is the same. The activity of all of these molecules is the same. They undergo this addition elimination because all of this carbon, I mean, this carbon is an electrophilic center. Why? Amines and alcohols, they're pretty good nucleophile because they have this lone pair of electron. Okay, so the challenge now could be to really try to draw out all the mechanism for each of these conversions to fully understand how these curly arrow they flow to make the new molecule. This not an easy example, but ethylamine, propanoic anhydride. First step, always the analysis, and then let's see how the mechanism goes. And this is another nice example of those addition eliminations, also called condensation, actually, because you can see we have two small molecules that come together to form a larger molecule with the loss of another molecule. So let's always think about functional group, always at the end, back to the basics of nucleophile, electrophile. Okay, very, very important. Good. So another good example, yeah, to analyze the mechanism and then to see a little bit the difference between a molecule that has a good leaving group and one that doesn't. So hydrogen, negative charge, clearly a nucleophile. And then, as we've seen, carbonyls, they pretty much react always in the same way. So we won't question it too much. It's an electrophile. Okay, what next? Really similar than before, nucleophile to electrophile, and the carbon double bond breaks because oxygen can do that. Okay, intermediate. And this is the intermediate, negative charge, because the electrons have moved on to the oxygen. So we always need to think about what those curly arrow means so that we can work out if there is any charge in the intermediate. And now, is there any leaving group? No, because we have just carbon-carbon bond, and then we have carbon-hydrogen, and those bonds break. In fact, in this next step, actually, we need the addition of another molecule, which is normally an acid, okay, because the only thing that could happen is that the oxygen, or even if it's present in water, this will occur, but normally an acid, it's added in this type of reaction, which we will see the name in a moment, to have, guess what? It's just an alcohol. So this is called nucleophilic addition. And this particular one, it's a reduction because we've added hydrogen and we turn an aldehyde into an alcohol. And in reduction, we always have first a reducing agent and then the addition of an acid because we need it in this step. And just to revise it, why not? The reducing agent used would be sodium boron hydride because it can provide that hydrogen with a negative charge.